Hi all. In this video, we see a special neural network architecture called transformer neural network architecture introduced in this paper titled "Attention is All You Need." So this is a neural network architecture where it is being utilized for formulating a ChatGPT with other component like a specialized training called unsupervised pre-training with supervised fine-tuning. So what this transformer neural network architecture is, it is solely based on attention mechanisms. So before we try to understand what does this mean by a solely based on attention mechanism, so we needed to have some background on some of the essential elements to understand these transformer neural architectures. So those essential elements are stacked recurrent neural network architecture, then statistical machine translation based on RNN encoder decoder mechanism, then how that initially formulated RNN decoder mechanism got some limitation due to the long sequences. Then this attention based mechanism is introduced on that RNN decoder mechanism. Then how does those things are utilized in other sectors like image captioning. Then finally, there are still limitation even though we are introducing the attention mechanism, RNN decoder mechanism. And finally they retain that encoder decoder mechanism, but they replace entirely the RNN mechanism and utilize only the solely on attention mechanism and formulated this architecture. I mentioned this is the encoder and this is the decoder. So before understanding this architecture, one has to understand what is stacked RNN. So we all know that the recurrent neural network has one hidden layer where it takes the input of the it takes the input and the previous hidden state and computes the present hidden state, and that present hidden state is utilized to predict the output for the corresponding time step. But in stacked RNN, like mentioned in this diagram, it has three hidden layers: layer 1, layer 2, and layer 3. And each hidden layer computes its own hidden state based on the previous time step and the previous hidden layer. And all those computer hidden layer hidden states are utilized to compute the predicted output. So this is a stacked RNN, and this paper introduced us already we have discussed about this RNN encoder decoder mechanism while we are introducing about the generative pre-training. So this paper, what does this paper says is they proposed some kind of a novel neural network architecture called RNN encoder decoder, where they have a two recurrent neural network component. One is encoder and another one is decoder. The encoder is something works on the input sequences one at a time, and all those informations about that input sequences are being extracted into a fixed length vector, and those fixed length vector was utilized in decoder mechanism to compute the predicted output one at a time. So this will be based on the conditional probability of the target sequence given a source sequence. So this mechanism is what been pictured in this diagram. This is an encoder and decoder, and at each time step or each instant, an input is given and the hidden state is computed, and finally that based on all those these representations being encoded in this vector C, and that this vector C is utilized to predict the output one. And this is what it's mentioned here, that they have proposed a neural network architecture card which can encode the information, which has a variable length sequence encode information to a fixed constant length vector representation, and those being utilized to make to predict a variable length sequence based on this conditional probability distributions, and is been trained to utilize this log likelihood estimate. And during those predictions, that hidden state all those informations in the input hidden states are encoded in this vector C, and that is being utilized in the decoder to compute the hidden state of the decoder utilizing the same like vanilla RNN that uh, that previous time step input and previous time step hidden state, and along with that the whole synthesis of the input sequence is encoded in this C. So this is the one. But what does this paper says is the same from the same group. They says that previously we encoded all those information into a fixed length vector, which is really a big bottleneck in improving the performance. So what does they try to do in this paper is they try to retain the same mechanism, but instead of putting all those information of the input sequence into a fixed length vector, they try to utilize all those hidden state informations in a systematically to predict in a decoder mechanism to predict the output. So what does this says is it's, again they says that it's very hard for the encoder decoder mechanism to only depending upon that fixed length output, especially for the test sentences which are longer than during the training corpuses. And this encoder decoder mechanism deteriorates rapidly as the length of the input sentences increases. So this will be an extension to that vanilla encoder decoder RNN model. And what the extension is something like the instead of that fixed length representation, it utilizes all those source sentence representation at each steps in a weighted average fashions that we will be seeing in this in this one. So what does this says is we know that at input sequence that every instant that hidden state is computed until the length of the input sequence. Those all those input sequences were being utilized to compute that input sequence representations. And as mentioned in the previous paper, only that final state output hidden state is utilized as C, and that is being utilized to predict the output in the decoder mechanism. But instead of throwing away all those information and only utilizing the final step, all these informations hidden in H1 to HT are utilized to compute this C. How that been compute is mentioned in this section 3. So for each instant decoding, that there will be that the corresponding representations will be computed, and that corresponding representation computed will be utilized to compute the decoder hidden state. That decoder hidden state will be utilized to compute the predictor output for the ith step. So how does this ith step input sequence representation is computed, called as context vector, is computed, is what mentioned in this equation, that it will be like kind of utilizing all those hidden states from 1 to t at that particular instant, and using some kind of weighted factors. This weighted factor is being computed utilizing these equations, and which depends upon EIJ. The EIJ will be depends upon how uh, that jth hidden state will be correlated with that decoder corresponding ith that input hidden state. So based on these correlations, this alpha ij will be computed. That alpha ij weighted factor will be utilized to give some weightage to that particular jth hidden state. So this will give you where to focus, and which jth word has to be focused, and which not necessarily to focus will be computed based on the values of this alpha ij. So by this, we can use all the informations of only throwing away the essential informations. This is what the logical behind this called the attention mechanism. That's what it's mentioned in all these beautifully written words. So this decoder having an attention mechanism, and it relieves the encoder from the burden of having to encode all the information in the source sentences into a fixed length vector. So therefore it is selectively that informations are retrieved by the decoder based on that ith step accordingly. So that will be depending upon how this probability of a alpha ij is computed, and that alpha ij value will be based on how that target yi aligned or translated from a source vector. It aligned with the source word xj. So how that jth position source word will be influencing that ith word output will be based on this alpha ij, and the alpha ij will be giving weightage to that jth word hidden state. So this is what the concept behind the attention mechanism. So this kind of attention mechanism is also utilized in the image captioning. It's the same kind of rnn encoder decoder mechanism as explained earlier. It has an encoder decoder mechanism, but here the encoder, here the concept is for that input image what kind of description has to be, sequence of words has to be described. So here the input image information is encoded by a convolutional neural network, and those features are being encoded in the AI1 to AL, like H1 to HT. Those features been captured through the convolutional neural networks, and these features, how much weightage patches of each AI1 to AL is a patches of images, local patches, and this which patch has to give weightage to give the description, the corresponding word descriptions will be based upon this representation of the image vector called z. This z is computed as mentioned earlier through this mechanism, that similar to that one last time we have mentioned. And that once that has been alpha from all those given some weighted average, and there will be some small transformations based on this, and that ct will be utilized in the lstm decoder mechanism to compute one word at a time, and at the end of that it will give you some caption description. This is called a soft mechanism. And hard mechanism is something like only focusing on a one among all those this representation. It will selectively choose the most important one, and that most important one will be utilized as the representation vector z, and that z will be utilized in the lstm to emit the captioning of the given image. The similar setup of hard attention and soft attention is being described in this paper. The same, it is neural machine translation. It's a stacked RNN where it is an encoder or decoder mechanism. And similarly, it has, as mentioned in the previous image captioning one, it has a global attention model. It means that soft attention where all those hidden state informations are utilized, and that corresponding weighted average is being computed, is what it's mentioned is like a soft mechanism. Here all the informations are utilized to compute this based on the correlation between that decoder hidden state and that particular jth word hidden state. And similarly, local attention mechanism is to selectively choose a few hidden states and having a bias on that, not giving an attention to all the one, only choosing a few among the hidden state based on certain setup, which we don't have to, which will not go deep into that. Only the thing is we understand that it's hard attention mechanism and soft attention mechanism, or a global attention mechanism, or a local attention mechanisms. So this attention mechanism is what utilized in this paper. It is some like kind of a stacked or multi-head attention mechanism is used to make and make some representation that is been fed into this our decoder mechanism. It itself has some certain kind of attention mechanism that we will be detailing possibly in the next lecture. And moreover, there is also an important paper called that's something, a way to replace an attention mechanism by another concept called active memory. And what does this says is there are some limitations in using some attention mechanism. and that limitation will be detailed in this paper. And what is the alternate remedy is to utilize another concept, which is a parallelizable one called active memory. And how does this active memory gets more benefits in compared to the attention will be have been described in this paper. Possibly we will go through this paper along with that active memory, and we will describe how that weighted average alpha ij is computed in this context without using an rnn encoder decoder mechanism will be detailed in the next video possibly. Thank you.